Hey everybody, welcome back to Fastware. So, we have looked at some memory allocators last time. So we looked at stack memory allocator, we saw its performance, it's doing great. You might be asking to yourself, well, that's sort of a very simple, maybe not even very useful allocator. I would disagree with you, however, I would agree that it is very simple. So today we're going to tackle something a little bit more complicated with a little more kind of a nuance involved. These going to be the pool memory allocators. So these are great for any objects of the same size, same alignment that you would want to store, right? The concept basically behind the pool memory allocator is you have a section of memory, which is continuous, and then you segment it into chunks of the same size. For instance, for 1 kilobyte, you want a chunks of 64 bytes. And then you weave basically a pointer from this pointer to next pointer to next block, right? So you always have a free head. So the pointer which points to the first free block. And therefore, when memory allocation is requested, you can just pull out that pointer, assign from metadata stored, which will be the next pointer, and then return that address immediately to the caller. So that's, as a concept, should be pretty simple. Imagine a linked list, a singly linked list, where you have a pointer next inside of a block. Similar concept. However, there are differences. So this implementation of free list is what is called a free list, right? So you can implement a pool allocator based on the free list, where the metadata about where is my next allocation, what is my next free block, is stored within the free blocks themselves. So the allocator only has a pointer to the next, and then when you do reference that block, it has a pointer to the next free block there, meaning that you pull out information from the block, you assign your next pointer, and then you return that block to the caller. Now, when you deallocate, you get a block, you basically override the memory there, saying that my current free block is some address. You put that address inside of the block that has been just given to you, and then you assign that new block to be available for you for next allocation. So this particular implementation of the free list, I think it's most popular because it's simple and it has great benefits to offer, meaning that the metadata information is stored within the free blocks of the allocator, and therefore it doesn't require any additional space, any overhead to store the metadata. However, it also does have a potential downside, where because the allocations as they occur usually occur on a memory that is cold, it is no longer in cache. You will basically need to dereference and store information into the cold memory. Therefore, your performance might be spiky. So for very small applications might not notice much, but it's definitely there. So actually, from my previous projects that I've been working on, I have a little something to show. I'm not going to show the implementation how they're done, but I do have implemented what is called the pool allocator and the section allocator. The section allocator is pool allocator, but implemented differently, which I will explain in a second. So, the section allocator, or the pool allocator that we will be implementing today, is based on the concept that we want to store metadata information together as close as possible to avoid these cold memory writes. We will sacrifice a little more space to store metadata separately. This gives us a lot more stable performance since the metadata is always hot in cache, and we don't need to touch the cold data separately. So this is the basic concept. And as you can see from the performance, so the standard pool allocator, this is using the free list concept, and the section allocator, which is using the metadata being stored separately concept, right? So notice that you have spikes of 8 nanoseconds here in on several sizes and whatnot. However, when you're using section allocator, that tends to not happen. You always have, high 6s, low 7s as your performance characteristic. So this is the basic concept, right? So let's go back to our implementation. Now, I have to apologize immediately. The reason being is I have implemented the entire pool allocator and I really didn't want to type it out again live on screen. So I have implemented, and what we will do is we will walk through, as there are a lot of concepts that I still have to show how they're done, why they're done that way, for it to make sense. Well, I hope that I will be able to explain it, that it will make sense. But to start with, we just have a pool allocator create info, exactly the same as we have the stack alloc create info. And this one has a parent, it has a block size, so not the whole size, but the block size, a block alignment to what we need to align. And then we have a block count, so number of them, right? So this is, I think, pretty simple. And the changes to the header are done. As you noticed, our API is able to handle this particular structure quite well. So let's jump into our implementations. I have introduced a new type of structure called memory address, which contains a union of raw address and a uint ptrt. Now, why did I do that? We do have, when we implement our own custom memory allocators, we do have to manipulate memory addresses quite frequently, add, subtract, multiply, all of these. So I have chosen to take this concept and encapsulate it into memory address, right? So I don't have to convert, cast the void pointer into something to add 64 bytes and then cast it back or whatever, right? What I want to be able to do is have a structure which allows me to manipulate one of these kind of indexes and the raw pointer being adjusted accordingly. This is the reason why I chose this, and I created, I know probably standalone functions would have been better, but I kind of wanted to show that we can use C++ concepts to actually do this by providing operator overloads when we need to manipulate addresses. Okay, so we have to our alloc type E, we have added a pool allocator, and we have implemented a pool allocator type. Now the pool allocator type, again, has a start and end to its address, its parent, its size. It knows how many blocks it has. It knows the alignment for each block, has the alignment as well. So it has aligned block size and the alignment. Have some shifty thing, diff shift, which I will explain in a second. And we have a block start, so this is our next free block. If you want to get a piece of memory, you will just ask this one and it will give it to you. And control blocks, this is where we'll be storing our metadata information. I've needed to debug, so I have added a little kind of a print statements where we print the internal state of the pool allocator. Since this time my implementation didn't go as smoothly as with a stack allocator, and actually I managed to introduce few bugs, which I spent a couple hours diagnosing and fixing, but finally it's all there. That's why it's very important to write tests, because without tests, I wouldn't have been able to find it. We have adjusted our aligned storage. Remember that we were returning a uint ptrt as a pointer. Now, for all addresses, any type of address will always going to be returning a memory address as an object, because it allows us to do very simple things. So take this example. This is the create aligned storage function. Look it up how it was done before, but now we can say, so here it is, we have a block address, we assign it to role. By the way, this is a XC extension, which is available for GCC, that you can assign to named variables by putting dot and then a variable name equals to whatever. For me, it's very convenient because I know that I'm not doing anything wrong. I immediately assign it. This is equivalent by doing this and then saying base address equal to raw. So these two statements are perfectly equivalent, but this C extension allows you to do in one line, which I prefer, generally speaking. Now, memory address allows to do some manipulation with these overloads that we have. You can say that base address plus a size gives us another memory address. So this is now adjusted memory address that we have. And this is a great pattern because, as you can see, we don't need to cast anything. There is no fluff around here. So it's very, very simple. So let's continue to see internal alloc. Let's see the create function first. Our pool allocator create function. First, we align our block. So we have a info providing block size and block alignment, and therefore we align one with the other. Now we have the aligned block size. The next thing what we want to do, say, is that block size a power of 2? That means, is it, I don't know, 8 bytes, 16, 32, 64, 128? We don't allow something intermediate, like for instance, if you want to have a 32 byte alignment, but you have, I don't know, 70 bytes, it would align to 96, right? Because 64 plus 32. So we don't allow that. There is a very good reason why we don't want to allow that particular pattern. Even though it might save space, you know, you save 32 bytes from 96 to 132. Sorry, I'm talking nonsense, am I? So what do we have? 64, 128. Sorry, yes. So the reason why we want to do that is because of that bit shift that I have shown and I didn't explain. If we can align to 2's complement, powers of 2, we can simply shift one memory address by an offset to arrive at the other memory address. This allows us to do quite beautiful things. And for that, I'll want to demonstrate this before we will move any further, because that concept is crucial to understand before we'll continue. So let me jump into the browser. And here I have prepared a little basic example. We have the same memory address structure that I just copied, and we have a difference, right? It doesn't, this just counts number of leading zeros, starting from the lowest bits. So these are the built-in compiler functions which translate directly into assembly. If you don't know, you can find GCC website. I will leave a link actually to it in the description, so you can have a look at all of these functions and what they do. But these are great. So this particular function, as I said, counts number of leading zeros starting from the least significant bit. So from the beginning, basically, right? And then when it encounters 1, it says we stop. We assume that both types are a 2's complement, therefore there will be only one. So basically only one said bit in a particular integer. So how we approach it. So difference would be calculated. So here we have a difference between a size A, which has an array of 16 integers, and a single integer. Imagine that this is our memory allocation block, and this is our control block. So our control blocks can be tiny, just maybe a pointer address to the next control block. And what we can do is something similar to this. So we have a start to our control block and start to our memory, usable memory for allocations. Now, let's say we found that the next free block is at the 100th element in that array. What we can do is take that 100th element address minus the beginning of the control block address will produce a memory difference. So this is the output. Please note, so assembly is here and here is the output. The memory difference is 400. And it's easy to see why, right? Because each block is 4 bytes, and this is at the 100th, so 4 times 100 is 400. Now, a diff size is a size difference between the size A and size int. So size of int is 4, size of A is, 16 times 4, so that's 64, right? And so we count that 4 only has, 2 leading zeros. This has 6 leading zeros. So 6 minus 2 leading zeros is that the shift, the difference between these two are 4 shifts, right? So shift right by 4. So given that we have a memory address and that difference, what we can do is take the memory offset by taking the difference for the addresses and shifting it by that difference in size. That will produce 6400 as an offset. Now, if we want to index into our new into our memory pool blocks, what we can say is the start of memory pool blocks plus that memory offset, and we found the element, this element, which is into our pool allocator blocks at the 100th element. So if you notice, I'm printing here the object, so object index, which we just computed, and object index B, which is at the 100th element. And 2 of these memory addresses exactly match. So we have 52051952, and both of them are exactly this. There is no multiplication, there is no division, there is no expensive operations to perform this particular operation. This is huge, because what you don't want when you're allocating memory or deallocating are expensive operations such as divisions, and a lot of the times multiplications when you actually have interlinked operations such as addition plus multiplication, so they are not commutative mathematically, right? Therefore, the compiler has to do one at a time. It cannot be done in parallel. Now, just to prove that this actually works, I follow by implementing the deallocation strategy, which is given now we want to deallocate object at 100. We say object B minus the beginning of memory address for it. We find the difference. So we find the difference between those being 6,400. Now we shift that difference by exactly the shift that we found before. So that's why we store it and not computing all the time. We shift back by 4, right? We shifted to the right. Now we're shifting to the left by 4. Taking the start of our control blocks and adding that newly produced value. And we find an object C, which by our calculations supposed to be exactly the same as an object. And therefore what we do is we find object C, we compare that these two are exactly the same, and voila, right here we produce exactly the same memory address, represented in decimal obviously, between those two objects. So now deallocation doesn't have to actually involve any divisions as well, which is magnificent. Let's switch back to our code. Since now I hope that you understand why we want to have our blocks to be power of 2 aligned. And we continue by saying that we have align block times block count. We figure out what will be our total space for allocation. We do exactly the same thing for control blocks. We say we have our memory address times, so these are 8 bytes, right? Times number of blocks. We know how much space we need for control blocks. We say that the allocator size, which we'll need to pass into our create storage, is our pool allocator plus the number of control blocks, so the size required for control blocks. And we create aligned storage. As we create aligned storage, obviously we take the base address, take the row of it, cast it into the pool allocator pointer. We produce the bit shift with exactly the same mathematics as you saw before between the align block and the memory address, which gives us a size to shift by. And we populate our objects, start with here. We take the address of the first block and put it as a block start. Then what we do here is just loop from 1 to block -1, block count -1, and we basically take the address and store into as a raw pointer the address of the next available block to know how to pick it up. And lastly, the last block, so info block count -1, we into the row we store a null PTR. If we come to that, means we ran out of memory, we cannot allocate anymore. So this is like a terminator at the end of the allocator, right? I hope I explained this enough and well. There might be one confusing thing. One confusing thing is this particular thing. You might be asking TSO, what is that? This is, again, an extension, a C type of extension, dynamic arrays, which you don't provide size, you just tell your compiler that I expect data following this object to be an array of this type. And therefore, now what we have is, instead of we saying how many bytes you want at the end and pointing with a pointer, we say that there is a block of memory after this object which will be allocated to store memory address objects following, right? It's sort of a little confusing. I don't know probably how to explain it well. But imagine that in our memory, as we allocate, I think as I showed here in the create function, we took the pool allocator plus number of control blocks. So that array. So this is for that array at the end. That concept only applies to the last element in the type. So it can only be declared array, as then all the data following that object is space for that array. Have a look, dynamic arrays. I will leave a link for you to read in a description below as well. So we'll come to allocate, I guess, because that's the interesting bit, how we do allocate. So internal alloc for pool memory allocator. So we take the size, required size, we align it to our allocator alignment, and then we say if our allocator block size is equal to that size that they're requesting, then we're fine. Otherwise, say that no, we cannot allocate that size. If it doesn't fit our required parameters, we don't care. We say that if block start is equal to null PTR, that means we ran out of memory. But we put a little kind of a caveat for a compiler to generate more optimal code. We're saying expect this to be false, that this condition is rarely met. And I think we all can agree that this is a correct way of approaching it, since most of the memory will always be there. It's just that last pointer, if we will reach that moment at all, we can, failure condition, have that cache miss, have that branch miss prediction, and expect to fail gracefully here. Now, this is a little bit gobbledygook, so be very careful as you read this. We take the start block and we take the raw memory address inside that pointer and we convert it to memory address. That memory address will be our next block. As I said, so you have like a linked list, right? So there's a next pointer inside of it. Now, what's next? We need to compute the address difference between the block start, so the currently available piece of memory, and where our control blocks start, right? If you remember that compiler explorer section, we basically did exactly the same thing. Then what we do is we produce the address shift. We shift that difference by our bit shift, and now we compute the offset address by taking available space where our objects need to be stored, as where our allocation is coming from. And we take that memory address and we shift it by that amount as we just computed. We obviously assign allocator the next available block, so the block start will be to the next block. And then we can return the offset address raw and the align size. So the implementation here is actually, if you're thinking about it, is actually very, very, very simple. There is no expensive mathematical operations, no divisions, no multiplications. Couple of subtractions, couple of additions, and basically a shift. So it should be really, really, really fast. And the allocate is somewhat similar. Again, we say, let's look at the block. If the aligned block is exactly the same size as a block, is fine. Otherwise, not our block probably. We take the block's pointer, we cast it into a raw, that's producing a block. We compute the memory difference between the block and the begin from where we can leach our memory, so our space for memory allocations. That difference then produces, so here we have a control block. So these are our control blocks. I just added into a single, so control blocks plus that memory difference plus the shift produces which control block we need to actually address. We extract that control block, and we basically reassign the allocator control blocks appropriately. This is pretty much it for pool memory. For pool memory allocator. So on deallocate all, we just need to basically iterate and reset how things are pointing one to another. We don't need to do anything else. Internal owns, again, just a range check. Preferred size is the aligned block. So if the size is greater than the aligned block, we basically say no. And if it is, so if the size is greater than our aligned block size, we return 0. If otherwise, we return the aligned block size. And we have a power of 2. This power of 2, as you saw we're using, is just built-in pop count. So the reason why we can ensure this, there's actually, as part, I think, of C++ 20, they will have the standard pop count, which if you look at their suggested implementations is exactly the same thing. Now, the reason why this works is just pop count basically counts number of ones in your integer, right? Now, when you have a 2's complement, a power of 2, only a single one can be in that integer. So if you think about 2's complement, so you have 2 to the power of 0 will produce 1, that's the first bit. Then 2 to the power of 2 that will 2 to the power of 1 that will produce 2, 2 to the power of 2 that will produce 4, then 4, then 8, then 16, then 32. And it's only a single 1 bit being set. You cannot have multiple bit set and still be a 2's complement. So therefore, we just count how many ones there are. If there is only a single one, we're fine. So it means it's a power of 2 object. So power of 2 size. And that's about it, I think, for the full memory allocator implementation. So I refactored a little bit our perf and our unit by separating unit tests into their own headers and doing exactly the same thing. Perf. So the pool memory allocator looks exactly the same thing. So the tests themselves, exactly the same thing as the stack memory allocator. We allocate with deallocate with our expectations. There is a code review open for you guys, which I will post in a description. Please go check that code review, have a look at all the changes. Leave comments to me on the code review and in the comments there to find out, to tell me if something is wrong. Ask questions if you're not sure about something. So that would be fantastic. And the last thing, what we have is our performance. So what we'll be doing is we have a pool allocator allocate, which only measures the time for allocations. And then we have our pool memory allocator deallocate, which doesn't count allocations, just want to see the deallocation, right? And we implemented also a free test. And so here is system free. So when we actually malloc, and then we measure the time for free. So I think it is high time to run our performance benchmarks and see how we've done. Voila, it finally finished. I had to sit there and wait. Luckily for you guys, just sped through. So what we have is our pool allocators allocate. So allocation takes about 1.5 nanoseconds in some cases. So when we have very small amount of objects, looks like we cannot warm up the cache just fast enough. So it takes a little longer, about 3 nanoseconds. But normally about 1.5 nanoseconds for allocation and about 1.3 nanoseconds for deallocation, which is pretty good. I'm liking that. Stack allocator's performance is slightly better in this particular case, but it's no surprise since it cannot deallocate. We don't even measure deallocations. But what we can do is just measure allocations, and it actually does slightly better than our full memory allocator. But it is expected since full memory allocator is a little bit more complicated. It's a tiny difference. However, we're still outperforming malloc with its 4.5 nanoseconds per allocation. Our worst case is about 3. And now for free. So free is about 6 nanoseconds at minimum. Sometimes even goes way beyond that with 8 and 9 nanoseconds. Now our pool memory allocator, Deallocate, so this bit, you notice the worst case is when we have very few objects, and then it scales towards the better cases, right? So you can see that the more objects we have, actually the faster it becomes. And this is great, because that's what it's supposed to be doing, right? You have many objects of exactly the same size. Imagine you have, I don't know, a map. I don't care. Something like that. So all objects there will be exactly the same size. So you want that allocation, to be super quick, super fast. And the allocation is exactly the same way. That's why the pool allocators actually are making into, I think, C++20 when they're trying to introduce pooled memory allocation inside of all node-based containers. At my work, where I work, they implemented their own standard library just to be able to do that, which brings great benefits opposed to when using malloc or new. So we looked at performance. Analyze it for yourself. Make sure that you understand that we've done everything correctly. We've done well. Our performance is 2 to infinity times faster. We destroyed malloc for both allocation and deallocation by avoiding multiplications and divisions. We're using a single shift, and we have an enforced requirement that our object sizes would be a 2's complement, basically a power of 2. And with that, please leave a like on the video. If you haven't already, please subscribe. Again, if you haven't already, I would appreciate that a lot. That helps my ego, helps the channel grow, helps me to put out more videos for you guys. And as always, have fun writing fast code. Cheers. Bye.